Today I'm going to be speaking about vertex calculations in condensed matter physics using Julia. So when you hear vertex, you might be thinking of something like this. So some geometric body, or if you will, some connected graph. And then the vertices are the corners of the tetrahedra, or the points where multiple edges in this graph intersect. So the objects that we will talk about today, they look a little different. They mostly look like this. So in general, when I say an endpoint vertex in the context of condensed matter physics, I mean a rank n tensor where the different indices x, they capture all the physically relevant degrees of freedoms, which are here denoted by alpha, beta, gamma, and so on. So why would we be interested in calculating such an object? So to explain that, I will briefly dive into strongly correlated electron systems, which are one of the current frontiers of condensed matter physics. So the difficulty when studying these systems is that they intrinsically require you to take a many-body perspective. So you cannot just treat the electrons as individual particles, but you really have to consider their collective interplay. And one of the simplest, somewhat realistic models that we have to describe them is the so-called Hubbard model, which basically consists of three terms in this quantum mechanical formulation. The blue term basically describes the movement of the electrons on the atomic lattice, as shown in this little sketch below. The red term is just the repulsion of two electrons of opposite spin when they sit on the same side. And then this black term basically controls the density of electrons that you put in your system. And although this Hamiltonian only has three parameters, T, U, and mu, you already find a variety of different correlated phases in them, including magnets, superconductors, and even more. So what we want to do in a theoretical computation now is we want to compute correlation functions to characterize these different phases. One example is shown below. This is a dynamical susceptibility, which basically describes the response of your system to an infinitesimal external perturbation, such as a very small magnetic field. And as you can see in this expression, in this diagrammatic formulation, the thing that we need to compute in order to be able to compute such an observable is a vertex function. Okay, let's take a step back and look at this object again, and let's do some naive scaling. So as I said, these x, they correspond to the multi-indices which capture the physically relevant degrees of freedom, and these might include the lattice index, spin, frequency, or more. So for this 4-point function, you could say, okay, that's great. That means that in the dimension of the different physical degrees of freedom, we will only scale, polynomially. But you already see it's to the 4th power, so the computational memory resources that we need to resolve that, they will actually grow quite rapidly. And if you go to higher order vertex functions, so you basically increase, the exponent, to higher rank vertices, you see that your scaling gets exponential. So in most applications, we actually restricted to computing these 4-point functions and not even higher order vertices. So before I show you some improved scaling, including the symmetries of a Hamiltonian, I first want to talk quickly about a method which we use to compute these functions, which is called functional RG. So the details of that method are not important. Actually, interesting part of this is that the vertex function is computed by solving a system of coupled ordinary differential equations, as shown here on the left. The special flavor of the FRG that we will use for the sake of this talk is the so-called pseudo-Fermion FRG, which is a special FRG method to treat quantum spin systems, for which there also exists a registered Julia package. So now what you need to do to integrate your differential equations is you will evaluate the right-hand side. And in order to do that, you need to compute these contractions that you see between these vertex functions, which means that you will need to sum over all the discrete degrees of freedoms that you have and integrate over all the continuous ones. At zero temperature or in real frequencies, for example, you would have to integrate, with frequency, sum of the spin, the lattice index, and whatever. And these integrations, they actually have to be carried out adaptively. If you don't do that, you see that you get these gross numerical artifacts for the asymptotics of your observables. And in addition, even for just moderately sized systems, the number of differential equations that we have to solve actually ranges between a few 10 to a few 100 millions. So we actually need quite some efficient code to do that. The good news is that all of the different components of your tensor can be computed independently. So the evaluation of the right-hand side and all of these contractions can actually be massively parallelized. The bad news is that, due to the adaptive integration and due to, different complexity of the diagrams on the right-hand side, the workload that we get will actually be highly asymmetric. So far, we only got the code to scale very nicely in shared memory, where we actually rely heavily on dynamic load balancing with Julia's threads.addSpawn. And we also need to, vectorize where possible to actually also make use of advanced vector instructions when switching to the cluster. And this we do by using the loop vectorization.jl package. So this is a quick example of how this calculation then actually looks like. I don't know if you can read this, but just in the overall structure, well, you have these different blocks that you see, these 4 blocks. These correspond to different complexity classes of the diagrams, and these are scheduled as individual tasks. So one thing that you can also see is that so far we were actually using thread local storage, which is now actually discouraged because it's unstable, because the threads might migrate between tasks. So actually, going to future versions, we will have to do some rewriting of that code to actually make it robust. Okay, so now let's come back to the scaling part, and let's actually talk about what we do to simplify the problem. So you can drastically simplify the whole calculation if you include the symmetries of your Hamiltonian. For example, remember that for this 4-point function, we would actually scale to the 4th power in the number of frequencies. But actually, if you include, for example, energy conservation, you actually only scale to the 3rd power, which is also nicely reproduced if we test the scaling with our code. So what's even more important is the use of lattice symmetry. So what I show here in the lower left is actually the number of lattice sites as a function of the bond distance for different 3-dimensional lattices. And you can see that using symmetries, the number of sites that you actually need to include is reduced by almost 2 orders of magnitude. And since, after all is said and done, the code scales quadratically in the number of sites, this is a massive improvement and actually makes the whole calculation feasible. So to end this talk, I want to quickly, show some results for our scaling analysis on different shared memories platforms. So here we have 4 different CPUs, 2 Intel, 2 AMD CPUs. Installed on different high-performance computing facilities in Germany. And as you can see, the scaling that we get is almost ideal on all the CPUs, except maybe for the Xeon Platinum. Actually, there, we were a little puzzled what's going on. So you see that the scaling falls off slightly after around 16 threads. But actually, when we benchmarked the single core performance on this CPU, we actually found that our code in single core runs is actually faster on this CPU than on the others. So we actually think that this might just be because the benchmark problem that we used to do the scaling analysis might be a little bit too trivial for the CPU to treat beyond 16 threads, because we don't have the full throughput on all the cores. But that might require some future investigations. Okay, so with that, I'm at the end of my talk. I thank you for your attention, and I'm looking forward to your questions.
All right. I'll take this one. This works. All right, we have time for a couple of questions.
Yeah.
Go first. Yep, sure.
That last scaling plot you showed,
Yes.
Was the workload floating point bound or memory bandwidth bound?
Well, yeah, I think it's actually memory bound more or less. Yeah. So actually, the operations that we're doing, they are not so heavy. But what I didn't say is that when you basically try to call this vertex function in the integration, you will have to evaluate it at points which are not necessarily in the grid, which you use to discretize, right? So you need to do some interpolations, and you need to access this thing, over and over and over again. So I think it's more it's a more of a bandwidth problem than I think the floating point operations.
Do you do anything for NUMA?
Yeah, we tried looking into that. So we started playing around with this and try to for example, allocate different parts of the array on different NUMA domains, so we can actually get better performance. And this gave us some improvement, but it was not as huge as we would have hoped in the end. But a few percent is still a few percent if you have to run a calculation for several days. So.
Hello, thank you. About the last slide before this one,
This one.
Did you perhaps test like using 2 CPUs on the same motherboard, like using in the
Sorry,
same node?
come again?
Did you test like using the same process but 2 on the same motherboard in the same node?
No,
Or this
so far,
scaling
no.
is only for. Is this scaling there only for 1 CPU or for 2 CPUs on the same node?
No, this is always using the full CPU stack of one node.
Okay,
Yeah.
so it might be that the node has 2 CPUs.
It might, yeah. So that might also factor into the
Oh,
scaling. Of
No, I'm asking because perhaps the Intel Xeon Platinum communication between the 2 nodes might be just bad, right? But 2 nodes, no, the 2 CPUs in the same node.
I can just tell because I know that bottom right system very well. So that's both sockets, both CPUs.
Oh, I see.
So,
Okay, so-
and there we don't see the drop. So
Yeah.
just saying.
But is this signalable? Because maybe the motherboard is
You can take it offline.
Might be.
No,
So we'll probably have to test it further.
Like,
So
was hyper-threading enabled in the
Sorry?
Hyper-threading, was it enabled in the
it was enabled in this run. Yeah, it was.
All right. We could do one more and then we would have to move on. Is there one more question?
Great.
If not, let's thank the speaker again.